Hi, this lesson is about Newton's method. So we use Newton's method to find the real roots, real number roots of an equation. Remember, roots can also be called zeros, and they can also be called x-intercepts because it is where the y values are equal to 0. So sometimes roots exist, sometimes they don't, but if they do exist, Newton's method allows you to get a fairly accurate answer with just a few calculations. So what I'm going to demonstrate here is a combination of using Newton's method and a little bit of a concept that we talked about with intermediate value theorem. So suppose that you have a function f of x that's defined in a closed interval where f of a and f of b have opposite signs. So if f of x is continuous on this closed interval, suppose here we have a and here we have b, and suppose f of a is a negative value and f of b is a positive value, then somewhere in between there has to be this root, this real number root. This is where it crosses the x-axis. So sometimes those are easy to calculate, but other times not so easy. So that's why Newton's method allows us to get a fairly accurate answer. If it's continuous and f of a and f of b are not opposite signs, then that means it didn't cross the x-axis within that interval. So assuming that f of a and f of b are opposite signs, then you can say that the first approximation is just the average of those two values. So that's what you would do when you don't know what your first guess is in terms of the root, is you would take the average of the two values of the closed interval, add them, divide by 2. So here's the formula for Newton's method. That's what you see right here, is that your second guess for the root is that x sub 2 is equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1. So that's your second guess. And the second guess gets you closer to what the actual root would be. But then you can continue and do it again and say that x sub 3 is equal to x sub 2 minus f of x sub 2 divided f prime of x sub 2. And that can go, that can continue. But usually by the time you get to x sub 3, your approximation is pretty close to what the actual answer should be. So let's look at an example. I'm picking a quadratic equation because I want to illustrate Newton's method, but also show you that you get really the same or very close to the same answer by just using the quadratic formula. So we're going to find the root of x squared minus 3x plus 1, and it exists somewhere between 0 and 1. And we're going to compute x sub 3 using Newton's method, and then we'll compare it with the quadratic formula. So first, let's make sure that we actually will find a root there. So we check the sign of f of 0. So f of 0 has a value of 1, that's positive. F of 1 has a value of negative 1, that's negative. So that means somewhere between 0 and 1, a root must exist. So our first approximation is the average of the interval 0 and 1. So 0 plus 1 divided by 2 means that my first guess for the root is 0.5. Then 0.5 is what you input into the formula. And remember, the formula was what I stated up above. So now my second guess for the root is that x sub 2 is equal to 0.5 minus f of 0.5 divided by f prime of 0.5. Well, when you plug in f of 0.5, you're just plugging it into the original function, which is your parabola or your quadratic equation. And remember, f prime, well, you need to compute what the derivative is, and that is just 2x minus 3. So you plug in 0.5 into 2x minus 3, and that's what you get in the denominator of the fraction. So x sub 2, when you do that computation, has a value of 0.375. So that's our guess for where the root exists. We're going to do it one more time as the directions specified, so compute up to x sub 3. So x sub 3 means that you use 0.375 inside the formula. So it's 0.375 minus f of 0.375 divided by f prime of 0.375. And when you compute that, you get an answer of 0.381944. Okay, so let's compare that answer, the one that we got with Newton's method, to what we would get if we use the quadratic formula. So if we plug in to the quadratic formula, you see that here, that's -3 plus or minus -3 squared minus 4 times 1 divided by 2 times 1. And that gives us 3 plus or minus root 5 over 2. Okay, so 3 plus root 5 over 2, that's outside of the interval from 0 to 1, but 3 minus root 5 over 2, that's within the interval. So when you actually compute that, you'd need a calculator to get this answer, but you get that 3 minus root 5, if you round off to the same number of decimal places as our x sub 3, you get that that's equal to 0.381966. Which is pretty close to what we got with Newton's method. Had we done Newton's method one more time, in other words, calculated x sub 4, it would be even closer to this answer here. Remember, 3 minus root 5 over 2 is an exact answer, and Newton's method gives us an approximate answer. But the more iterations you do of Newton's method, the closer you get to the exact answer. All right, so let's do another example. This is a fourth degree polynomial, and we want to find the root between 2 and 3 for x to the fourth minus x cubed minus 3x squared minus x minus 4. So again, I'm going to check to make sure a root actually exists there. So if you plug in f of 2, you get -10. Well, that's negative. If you plug in 3, f of 3 is 20. That's positive, which means somewhere between 2 and 3, a root exists. And so our first guess is just the average of those two numbers. So 2 plus 3 divided by 2 means that our first guess is 2.5. And then that will be our input into our Newton's method formula. So we have x sub 2 is 2.5 minus f of 2.5 divided by f prime of 2.5. So just like the last example, you need to figure out what f prime is. So that's 4x cubed minus 3x squared minus 6x minus 1. So you would be plugging in 2.5 into that derivative, and that's what you get in the denominator of the fraction. So when you compute that all, you get 2.5653 as your approximate root. Okay, but we're going to do that calculation one more time. Again, x sub 3 usually gets you pretty close to what your answer is. So x sub 3 is equal to 2.5653 minus f of 2.5653 divided by f prime of 2.5653. And when you do that computation, you get 2.5616. All right, so here we can't use another quadratic formula, for example, to compare, but I'm going to show you the graph. The graph of this polynomial is here. I used this website to graph it. You can use a graphing calculator if you'd like. And so you can see that Desmos.com gave me a graph where it shows that the root between 2 and 3 is about 2.562. So our Newton's method gave me an even more precise answer than what the graphing calculator app gave me. So now you should try the homework. You definitely will need a calculator to do this work.